Consider the following data for this reaction, and we're given data from 3 experiments here, and asked what is the overall order of the reaction and to determine the rate constant. So this is a classic example of how to determine the overall order using experimentation. So our rate is going to be described by an equation, which is our rate constant K multiplied by our concentration of A raised to some power m, multiplied by our concentration of B raised to some power n. And what we want to do in this problem is figure out m and n, because this will tell us the overall order of the reaction. So what we can do is first choose 2 experiments from our list. And we're going to use the ratio of the expressions that we develop to simplify and solve for m or n. So the experiments that I'll choose is experiment 1 and experiment 2. And that's because our concentration of component B, which for convenience I'm going to call this reactant A and this reactant B, these concentrations are the same, so our n variable will end up canceling and it'll be easier to solve for m. So I'll show that in the calculations. I'm going to write out the expressions for the rate equation for experiment 1 and experiment 2. So for our experiment 1, our expression is our rate constant K times our concentration of A raised to some power m, and I'm just looking at this data here, times the concentration of component B raised to the n equals our rate, and we're given our rates in this column here. And then I can do the same thing for experiment 2. This is just following the same type of expression. And now that we have these 2 expressions written out, we can take the ratio of them, and our K's will end up canceling out. Our concentration of B will end up canceling. And so we're left with an expression to find m, and that can just be described in a more simplified manner, which I'll write here. And when I solved this, I ended up getting that m equals 1. So this is telling us that with respect to component A, the reaction is first order. We need to know with respect to component B what order the reaction is so we can find our overall order. So we're going to do a similar process for n, to solve for n. So I'm going to pick another 2 experiments to solve for n. And I'm going to pick experiment 2 and experiment 3. And this is so that my concentration of B won't end up canceling out, and in this way I can get a value for the unknown variable n. So it's going to be a really similar process. So for experiment 2, I will write out the equation. We have K times our concentration of A raised to m, and we found what m is, so this is just raised to 1, times our concentration of B raised to the n, and we're given our rate. And we can do the same thing for experiment 3. So in a similar way, I'm just going to take the ratio of these expressions. The K's will end up canceling out, and then my only unknown is n. So I end up getting that n equals 1. And similarly, this is telling us that with respect to component B, the order is 1. And so now that we have both n and m, we can figure out the overall order. So I will write out our rate expression. We have r equals k times our concentration of A raised to 1 times our concentration of B raised to 1. So this equation is telling us that with respect to A, the reaction is first order, and with respect to B, the reaction is first order. So overall, we have a second order reaction. And it's important that it does say overall, because a problem may ask you, with respect to component A, what is the order? But this is asking overall. So now that we have that, we can determine the rate constant, and I'll just call this part B. So we're just going to do this by picking one experiment to solve for K. We already did most of the work, so this won't be as calculation intensive. So I'll just pick experiment 1, and I know that my rate is K times the concentration of A times the concentration of B, and this equals our rate. And so if you solve for K using this expression, I end up getting that K equals 4.98 times 10 to the negative 3 inverse molar times inverse seconds.